12.3. We'll even get into 12.4. 12.3 is on the dot product. I did want to put down the dot product equation that you'll see. Well, it's on the formula sheet, but we're going to find that very useful. Is A dot B is equal to the magnitude of vector A, the magnitude of vector B, times the cosine of theta. All right, that's a dot for dot product, and the dot product is scalar. We don't have to write the formula down for computing a dot product, right? Like when we did before, right in the last class, if we had to dot this vector with this vector, what would we get? So this is vector A, this is vector B. We took the dot product A dot B. We get a scalar value, right? We get a scalar. And we just do 1 times 2 plus negative 3 times 1, negative 3, plus 2 times 0, right? And that's how you do a dot product. That times that plus that times that plus that times that. And if it's two-dimensional, all right, that times that plus that times that. It's great. Usually you could do it in your head, right? Usually you can do this. What is the dot product? 1 times 2 plus negative 3 times 1. I'm writing it all out, but I bet everyone in this group right now, this room, can just do all this in their head. What do you get for the final answer?
Negative 1.
So dot products can be negative. I wanted to point that out at first. I don't want you to think dot products always come out to be positive, but it's not a vector, is it? All right. But this is a wonderful, wonderful equation that we're going to use throughout this course. Start. Oh my God, that one's important. There's one that looks like this with the cross product. Cross product is what we covered in section 12.4. Maybe we should write it right underneath. So this is the dot product of two vectors. Well, why is this important? Number one, it can tell us about two vectors that are perpendicular to each other at 90 degrees, right? See, what's the cosine of 90 degrees? Where theta, by the way, in that formula, theta is the angle between the two vectors. What's the cosine of 90?
1.
Cosine of 90 is 0.
0,
right? The cosine of 90 degrees is 0. So that's telling us that the dot product of two orthogonal vectors, if you want to use the word orthogonal, if you like perpendicular, that's fine too. But two vectors that are perpendicular to each other or orthogonal will always be what? 0. So that's important. Like A dot B equals 0. Well, that means vectors A and B are, I use that perpendicular symbol, right? The upside down. They're going to be orthogonal vectors.
So it's like key statement. If A dot B is 0, then they are orthogonal.
That's right. That's right. If A is orthogonal to B, then A dot B will always have to be 0.
0.
Are these two vectors orthogonal to each other? No. We just saw it. How about those two vectors? I mean, these are in three-dimensional space. We're not even drawing them, but the angle between those two vectors. 90 degrees. It'd be 90 degrees because the dot product is 2 plus negative 2 plus 0 equal what? 0. So these two vectors are orthogonal to each other. The last two, they were not orthogonal. I'm curious about these two vectors though. They're definitely not orthogonal. 2, 3, 4, vector B. 4, 6, 8. Can you tell me about these two vectors? They're definitely not orthogonal. What are they? I heard it. What are they?
Parallel.
Parallel. So how can we tell two vectors are just parallel to each other? This thing won't help us much, right? That was for perpendicular. But one will be a scalar multiple of the other. And that means you can think of this as what? This right here is 2 times vector A. And so that's how you can tell whether or not two vectors are running in the same direction and parallel to each other. If one is a scalar multiple of the other. That means, if this helps, it means all the ratios between the corresponding components should be equal, right? So if that helps, look at the ratios. You want to know they're parallel? Two vectors parallel, all the ratios should be equivalent. Let's look at it. Is 2 over 4 equal to 3 over 6 equal to 4 over 8? Yes. And so these two vectors are parallel. So no matter how they write it, that's how I can tell whether or not two vectors are parallel to each other.
In 3D, you cannot do slope, right?
That's right. The slope will be important, Art, and especially in 3D. But what's great with these vectors is we'll always use vectors to help us identify things like this. Whether or not you got what? Vectors running parallel. You know, perpendicular. Remember when we did what? The college algebra course? It was like they said, oh, you had to do like, one slope was 3/2, the other slope was what? -2/3. But that's because everything was nice in two-dimensional space, and we had a y equals mx plus b. And today, if we get into it, section 12.5 does deal with straight lines that are three-dimensional, and lines going through three-dimensional space. But again, what we'll look at is, we won't look at that m, we're going to use the vectors. And we'll use this concept, this concept that vectors perpendicular or orthogonal have a dot product of 0. Okay, so this is really important. What else is important about this formula? This allows us to find angle between two vectors. Oh, that's huge. So this formula right here allows us to determine what is the angle between two vectors. So let's try that. Here's a vector, 2, 4, 1. Here's another vector, -3, 2, 0. Now I was wondering, these are in three-dimensional space, right? These are three-dimensional vectors. What is the angle between these vectors? We'll use this. It won't be hard, but we should rearrange that formula and solve for theta. Can you do that? Well, let's just see. What would cosine theta equal to? A dot B over the magnitude of A, magnitude of B. I mean, you might write that as a separate formula in your notes. And that's what cosine theta always equals. But let's improve that. I want you to find the angle between the two vectors. What would they be? How can I write this?
So first you do the dot product on the numerator, then calculate the magnitude and multiply.
And there you go, inverse cos. So very good. I'm going to put this and just stick all this in there. But let's start out. What is A dot B? -6 plus 8 plus 0. Is that a 2? Does everyone agree for A dot B? What's the magnitude of it? This is good. So we're all going, oh, this is stuff from yesterday. How do you get the length of this vector?
21. You
You
add
need
on
the square root of that square plus that square plus that square. We have a little square root. Square root of what?
21.
All right, 21. Put a hat on it. Whoops. And then I'll put just multiplication sign if you want. Not a dot product, just a star multiplication times what's the length of the other vector?
30.
Yep. Magnitude squared is 9 plus 4 plus 0 squared is the square root of 13. Let's type this in our calculators. Let's put it in degree mode. So does anyone know how to change it to degree mode? I want to point out, you know why I type this in? I always try to avoid as many parentheses as possible. If you put a parentheses here, doesn't your calculator automatically put a parentheses here? I mean, you got to end it. You put one here, then you got to what? Close it. This is how I type it in if you're curious. I'll do this. 2 division square root. But on my calculator, before I type this in, I'll just figure out what the heck is 21 times 13. So what is 21 times 13? I'll just make one radical. What is that? It's like the older TI-84 model. Somebody had the upgraded cool TI-84 where it like puts it in math print mode. I don't have math print mode. So this is how I'm safe. I'll type it like that. You gotta close that parentheses.
As long as I type it like that, I'm going to check my mode, everyone. Oops, I was in radian mode. I'm going to change it to degree mode. And I'm going to hit inverse cosine, that's second cos. And then a 2. Division. Square root. 273. What do y'all get? What's the angle? It's about 83 degrees. I'll squiggle. Right? Not 90, close to 90, but this is throughout this course when you're like trying to find an angle between two vectors. Reflect on that. Go, wait, I know it. There's a way to get this. Just manipulate that. Cool. All right. Well, that's pretty cool. So we can find the angle between two vectors. But I'm looking at this. This is a problem like the problem from the practice set. What if he gave you 3 points, which forms a triangle? How could you find like one of the angles in there? Okay. So this is like number 7. From here, you go, well, which one from the textbook? From the textbook, when they're asking for the angle between the two vectors, they actually put a problem like this. Oh, it's in section 12.4, but you'll see it. So let me just make up some points here. How about 0, 1, 2? Now that's a point. We can call it point P. Point Q. What? 7, 9, and then a 16, and then point R. Okay, point R is, let's see, 1, 5, 9. Can you find the interior angle between vectors PQ and PR? That's the question. Can you find the interior angle between vector PQ and PR? So looking at a picture, and we're talking about like, there's PQ, there's PR, not drawing the scale, but can we use that formula? You bet. We'll use it. What's the magnitude of PQ? Oh wait, before I even start, what is vector PQ? I apologize. To go from points to vectors, points sometimes look like vectors. Don't let that confuse you. I have to find the vectors first, right? So what are the points? 0, 1, 2, 7, 9, 16. Tip minus tail? All right, what's vector PQ?
Negative 7. Negative
7?
No, negative, right?
Well, if I do
Oh,
tip minus
7,
tail,
tip minus 8.
7 minus
And
0.
0,
So I got you. You were doing vector QP. But I'll do 7 minus 0,
Yeah.
9 minus 1, and 16 minus 2. Is that 14? All right, what's PR? One, 4, 7. Sorry I made this up. We didn't get any negative values. Sometimes we can get the negatives, right? So there's those. Now what are these magnitudes? 7 squared plus 8 squared plus 14 squared. What's the magnitude of PR? 1 squared plus 4 squared plus 7 squared. But I'm still going to find this angle to be inverse cosine. The dot product of the two vectors times the magnitude of that and magnitude of that. If you don't mind, can you let me know what that number is under the radical? That's pretty big. Woo! 49, 64, and 196. Ooh, thanks. And then the other one? Oh, we can do that. What's 49, 50, 50 plus 16?
66.
Cool. Now what's the dot product? 7 plus 32 plus, what's that, 98? What's that come out to be? Is that 137? Is that right? For dot product? I'll let y'all check that. That's right. That's right? Well, this will give us the actual angle. Now, you don't have to enter that on your calculator now, but do you agree? That's how we go to find that interior angle. It was using this powerful formula right here, this little equation. To say I'll get the dot product of the two vectors, I'll get the magnitude of each vector. What was key though, we had to get the what? Figure out the vectors from the points first.
Excellent. Hey, I don't think we have to work out this problem, but we can talk about it. A problem on this worksheet. They asked about this. I want you to just explain to me what to do. Number 9. They go, which of the following vectors is orthogonal to both A and B? I mean, what's one thing you could check in all the A, B, C, D, and E? Check to see which ones have dot products of what? 0. Great. I do want to point out you're going to learn something today in 12.4. You might find it easier to work that problem. If you're like, I don't feel like checking all these out with the cross product. But right now, you know that dot product of two vectors equals 0 means they're orthogonal, right? You could just go through them all and check them. We do have to talk about number 8, however, which deals with the vector projection. So I want to talk about that. There's something that emerges in this section 12.3. CUMP, B with an A here, and this is called the component of B along A. I'll even write it over here too. Component of B along A. It equals A dot B over the magnitude of it. That's what it's equal. I'm going to draw a picture so you can make sense of what this would look like. First of all, the component of B along A, that's what it's called. It's a scalar value. You all agree. Look at the formula. It's a scalar. All right, so that's a scalar value. It's just a number.